Hello everyone, let's continue with our final and localized whitewater tweaks and wedges. So in the previous video we explained like initial and main tweaks for whitewater solver, and we defined the attribute that we like and also value for this attribute. But now we want to go a bit further and tweak some of these main attributes, for example like repellent, and try to get our phone to look as close as possible to our reference. So the first wedge in this video is going to be repellent noise. I already explained what the noise and how the noise range is going to help us to break that uniform circle look of our foam. So let's see the preview, and for this preview I use the noise range 0.25 to 1, then 0.4, 0.6 and 0.9, and you can see how already the foam lost that perfect circle motion. And these other videos is just to see how much of the actual noise we are going to use for our final simulation. So in our whitewater solver, the final value for the noise range was 0.4 till 1. And the next wedge that I did was I was trying to break that uniform size for our repellents that are going from from 0 to 1 or 0.2 to 0.5. and the attribute that I explained in the intro video is match distribution. So match radius distribution, this is how with this value you can break that uniform look and maybe use more of the minimum value and less of the maximum value, and then add somewhere in between, just that we break that uniform type of look that are going from one value to the other. So the first one is with match distribution radius off, and these other three are just different look of the ramp, so radius distribution ramp, and how they are going to affect our simulation. So if we see the preview, so this is default one with off, and you can see like going from 0.75 to 2, and on the other, as you can see, we can see variation. Somewhere is bigger, somewhere is on some areas is smaller. For example, if you compare this area to this area, you can see variation big, then less big, more smaller, but here is more or less that uniform type of look. And if we see in our reference, there is a lot of random size of our foam pattern. So here is the few big ones, then a lot of smaller, and this match distribution is going to help us to achieve that type of look. The next wedge that I did is actually repellents by speed. So the one at the end I didn't use, but I just wanted to see how much this attribute is going to break our simulation in terms of that uniform look. And the biggest visually change is when I use the value from 0.0 to 1. So as you can see, the speed over the value of 1 is not going to be affected with repellent, and at the end this result looks really interesting because you can see this area, they don't have the they are not starting to form the foam, I mean the foam cellular type of look. And if we compare with the reference, we can see on the same thing on few of this area, like here, that this is more or less like a diffuse type of foam that is just advecting with with the fluid motion, and less is already starting to form, that cellular look, as you can see here. So the speed range can actually help a bit, so you just need to find the proper value. So let's play one more time just to see. So this is different range for the speed, but only the one that visually show the biggest difference is the range from 0 to 1, as you can see here, and can really break that uniform look, something that we have, for example, on the last wedge. So if you like it, you can use this speed range that can really, it's giving really interesting visual look. The next one is a drag animation and the noise velocity. So drag animation is that I wanted to slow down the particles in this area. If we see at the beginning in our reference shot, the particles just more or less really slow, don't fly too much away from the whale. They just slide down, or over the body of our whale animation. So I wanted to minimize these crazy particles flying away from our whale. So what I did is that I just used pop drag global and just animate at the beginning of our simulation to be like stronger value. As soon as the whale soon as the particles break from the whale body, I go back to initial value that was 0.025, and these are different strength values. And then something that I didn't like, and something that you can see on our reference a bit, is that particles that fly, they don't just fly in one direction, they just move a bit of left and right, or catch by the wind, so they're just not, there is not that uniform motion just from A to B. So I try to introduce a bit of random velocity between the fluid surface and also like our final depth of our spray. As you can see here on the final simulation, I add a bit of noise just to break that uniform look. So if we check this top two wedge, you can see the difference, that when the splash happened, the particle just go and nothing, they just fall down. But in these two other wedges, you will see how velocity is going to break that motion and make it more spray and crazy mist. I maybe use too much, but I just want to see visually what is going to happen if we add this type of effect. So in depth setup, so this is actually noise, but mid depth. So I use depth attribute that is on whitewater solver, and I use value from 0.2 to 0.5 and just use the ramp. So at the beginning of our depth, that is 0.2, there is no actual noise, and close to the maximum value of our depth also there is no. So in between, so it's like noise based on medium depth, we are going to add noise to our initial velocity value. So I just use simple noise and multiply it with that depth value with the ramp, and just add to our already velocity, and this is going to give us that break with this spray mist particles. And I really like the result, and at the end I was tweaking to find the values that I like for that noise. But you can see the difference between these two. This is like totally not moving, just splash happen and they just go into direction and fall down. But here they are break and add also that inner motion. So for the next wedge, I was trying to achieve one effect. So if we see here in the reference, is that when the splash happened, only the big splash, you know, parts are flying pretty fast, and everything else that, you know, becoming the mist is, you know, slowing down and go, you know, behaving almost like a trail. So I wanted to, you know, because we have that adhesion effect and the fluid is going to stick to our surface field, but I also want that these spray particles don't follow that surface field that's strong, they just, you know, stay behind, still have the same initial speed, but just behave like these, you know, really light and, you know, mist particles. So for this I use, you know, pop drag based on depth. Sorry, you know, I mistyped here. So pop drag based on depth, and, you know, these are two different values. So we can see here, and the splash happen, as you can see here, we can see that effect, that only the adhesion, you know, particles that are follow the surface field are flying the same speed, but the other one, they leave like a trail, something that we have here on our, you know, reference. And then the other solution that I also try is to, instead of using drag node, I use, you know, custom node just to multiply, you know, initial velocity or, you know, speed by depth, the similar that I use the depth value on the drag node, but instead of that I just multiply by initial velocity speed. So you can see here it's a bit different result than actual using drag. So this is, you know, like almost there is no effect, but, you know, from value of 0.92 to 1 is something that are going to show you some visual difference. And inside of DOP simulation, the simple, we again are going to use, you know, our depth attribute. So this is going to be our minimum and the maximum depth value. So we just want to slow the particles that are far away from our surface field, so more or less the spray misty one. So with our minimum depth, the speed of our particles is going to be original 1, and the soon as the particles are far away from our, you know, surface field, we are just going to multiply our velocity with 0.97. So just slight slow down, and this is going to give us similar effect like, you know, pop drag, and something that we are trying to achieve to get closer to our reference. And the last one in this set of wedges is depth range, and I want us to see how visually the depth range is going to change our simulation and also affect our simulation loop. So if we go back, the depth range is actually located here and that's the part, that's the value that, you know, around our foam layer. So I wanted to see if I change, you know, this, you know, depth range and how it's going to look. So depth range here is 0.25, 0.5, 1, and then 1.5. And let's see how it's going to look. So you can see visually when the splash happened, this is on the low depth range, this is behaving more like, you know, spray. But with the higher value, this is the fluid is, you know, attracting by adhesion and repellent already. And then when the splash happened, we can see that bigger depth range is going to affect our spray part, but also we are already can see that effect that I was trying to get in our reference when the splash happened, that we have only the bigger parts flying pretty fast, but the misty one are just following that simulation and slow down. So with that range we can visually see that effect, but also what kind of problems can happen. That range over 1 is, for now, it's in our simulation it's too strong, and our simulation don't look nice. So values from 0.75 to 1.2 is something that can look interesting for our simulation, and I suggest that you try this and compare when you start tweaking your own simulation. I hope you like it so far. These are the main tweaks and more localized tweaks that we are going to do for this video. Thank you, and see you in the next one. Bye.